The late spring air hung thick with tension in the depths of Whitehall. May 30th, 1942, marked a turning point that nobody in that stuffy conference room could have predicted. Deep within the British War Office, shadows stretched across polished oak tables. The smell of tobacco smoke mingled with the musty odor of old leather and bureaucratic anxiety. Admiral Louis Mountbatten entered the room with measured steps. His uniform was crisp. His bearing spoke of naval tradition. Around him sat the most experienced military minds in Britain. These men had studied warfare for decades. They understood the mathematics of destruction. They knew the limits of what armies could achieve. The admiral's voice cut through the silence like a blade through silk. His words seemed to defy reality itself. If ports are not available, we may have to construct them in pieces and tow them in. The statement landed in that room like a physical blow. Silence stretched for exactly 3 heartbeats. Then the eruption began. Laughter exploded from every corner. Deep belly laughs mixed with snorts of derision. Hoots echoed off the walls. Jeers bounced between the assembled officers like bullets ricocheting in a confined space. These weren't junior officers easily impressed by wild schemes. These men had witnessed the carnage of the Great War. They had seen what happened when theory met the brutal reality of combat. They understood harbor construction. They knew about physics. They comprehended the savage nature of the English Channel. The very concept contradicted everything they had learned about warfare. Build an entire harbor from nothing. Transport it across the most dangerous waterway in Europe. Assemble it while enemy artillery shells rained down. Complete the impossible task within days rather than years. Pure madness. Complete insanity. Yet somewhere in that moment of ridicule lay something extraordinary. The seed of what would become the most audacious engineering triumph in military history was taking root. A project so ambitious, it would completely rewrite the rules of amphibious warfare. An undertaking that would shatter every assumption the German High Command held about Allied capabilities. The mathematics of D-Day's ultimate success were being written in that very moment. Not just in battle strategy and troop movements, not merely in intelligence gathering and deception operations, but in concrete and steel, in hydraulic systems and precise tidal calculations, in the revolutionary concept that impossibility was simply another engineering problem waiting for the right solution. The catastrophe had arrived like a thunderclap on August 19, 1942. The blood-soaked beaches of Dieppe became a graveyard for Allied hopes. Over 6,000 Allied troops, predominantly Canadian forces, had stormed ashore in Operation Jubilee. The operation was carefully designed to test German coastal defenses. It was meant to demonstrate Allied resolve to Stalin and the world. The assault transformed into a massacre within hours. German machine guns positioned in massive concrete bunkers atop gleaming white chalk cliffs cut down wave after wave of attacking soldiers. The sound of automatic weapons fire echoed across the water like deadly thunder. Bullets whistled through the morning air with mechanical precision. 27 Churchill tanks rumbled onto the shingle beach with grinding determination. Every single one was destroyed or abandoned before the day ended. Steel burned. Ammunition exploded. Men died trapped inside metal coffins. Of the 4,163 Canadians who embarked that morning with hope in their hearts, only 2,210 returned to England. Many of those bore wounds that would never fully heal. The final casualty count staggered military planners across the Allied command structure. Canadian casualties alone reached 3,367 men. Among them, 916 lay dead on French soil. Another 1,046 faced years in German prisoner-of-war camps. The Royal Navy lost 75 killed and 269 missing or captured. The Royal Air Force suffered 62 fatalities in the skies above Dieppe. German casualties barely exceeded 600 men. The entire raid lasted less than 9 hours, from first landing craft hitting the beach to final evacuation under withering fire. Those 9 brutal hours taught the Allies the most expensive lesson of the entire war. Any future invasion of Fortress Europe would absolutely require capture of a major port to sustain the massive assault forces needed for victory. Yet Dieppe proved beyond any shadow of doubt that German defenses made direct assault on a fortified harbor completely suicidal. The concrete was too thick, the artillery too well positioned, the machine gun nests too cleverly concealed. Major General John Hamilton Roberts commanded the 2nd Canadian Division during the Dieppe disaster. His after-action report, discovered decades later buried in the National Archives, revealed the stark truth. The strength of German port defenses exceeded every intelligence estimate by enormous margins. Concrete casemates housing heavy artillery proved completely impervious to naval bombardment. Machine gun positions enjoyed interlocking fields of fire across every possible approach route. The port facilities themselves were meticulously prepared for demolition at the first sign of any attack. Even had Allied forces somehow captured Dieppe intact against impossible odds, German counterattacks would have reclaimed it within 48 hours. The strategic paradox became completely inescapable. The Allies desperately needed a port to successfully invade Europe, but the Germans had systematically fortified every single port from the fjords of Norway to the Spanish border. Millions of tons of concrete and steel transformed each harbor into a fortress. The Atlantic Wall was becoming reality rather than propaganda. Field Marshal Erwin Rommel received his appointment as Inspector General of Atlantic Wall Defenses in late 1943. He had transformed Adolf Hitler's propaganda boast into a genuine obstacle that could stop armies. His reputation for aggressive action preceded him to every bunker and gun emplacement. By December 1943, Rommel had completed his comprehensive 2-week inspection tour of Atlantic defenses. His eyes missed nothing. His engineer's mind catalogued every weakness. His confidential assessment, preserved in German military archives, revealed deep concerns about what he discovered. A basic concept for defense did not exist in any coherent form. The precautions already taken did not meet the seriousness of the threatening major landing operation. His solution was characteristically aggressive and methodical. Rommel immediately ordered the emplacement of millions of mines along every potential invasion beach. He demanded concrete pillboxes at every strategic point where enemy forces might gain a foothold. He personally supervised the installation of beach obstacles specifically designed to rip the hulls from landing craft. Rommel's asparagus sprouted across fields behind the beaches like a deadly crop. These tall poles with sharpened tops would impale gliders and paratroopers attempting to land. More critically for Allied invasion planning, Rommel systematically fortified every port along the coast. In a secret memorandum to Hitler dated December 31, 1943, Rommel outlined his strategic thinking with characteristic clarity. The focus of the enemy landing operation will probably be directed against 15th Army's sector. It seems highly likely that the enemy's main concern will be to get the quickest possible possession of a port or ports capable of handling large ships. Hitler responded by designating 11 major ports as Festungen. These fortresses would be defended to the last man and the last bullet. Dunkirk, Boulogne, Le Havre, Cherbourg, Saint-Malo, Brest, Lorient, Saint-Nazaire, and the Gironde River estuary leading to Bordeaux all received top priority for men and materials. The Channel Islands joined this list of impregnable fortresses. Each fortress boasted heavy naval guns mounted in reinforced concrete emplacements. Artillery batteries covered every possible approach from land and sea. Anti-aircraft positions bristled with weapons. Minefields extended for miles into the surrounding countryside. Garrisons prepared psychologically to fight to the death rather than surrender. The German defensive philosophy rested on an assumption so fundamental that no senior commander ever questioned its validity. Any invasion force absolutely required capture of a major port within days of the initial landing. Otherwise, they would face inevitable defeat through complete lack of supplies and reinforcement. This assumption had governed military planning since ancient times. Armies needed harbors for their supply ships to dock safely. They required dockyards for essential repairs to damaged vessels. They needed cranes for unloading heavy equipment and artillery pieces. They demanded warehouses for storing ammunition and provisions. Most critically, they needed protection from the violent storms that could scatter and completely destroy an invasion fleet. General Dwight D. Eisenhower received his appointment as Supreme Commander of the Allied Expeditionary Force with full understanding of this impossible strategic situation. In his personal diary entry from March 1943, he captured the dilemma with crystal clarity. We face a choice that offers no acceptable solution: attack a heavily fortified port and suffer catastrophic casualties in the frontal assault, or land on open beaches and watch our supply lines collapse within weeks of the initial success. Either course of action leads inevitably to complete defeat. The alternative that emerged from the failure at Dieppe may represent our only realistic hope. Though it defies all conventional military wisdom accumulated over centuries of warfare, what Eisenhower called the alternative had begun germinating in the brilliant minds of British engineers even before the Dieppe disaster unfolded. The revolutionary concept traced its intellectual roots back to 1917. Winston Churchill, then serving as First Lord of the Admiralty, had proposed using flat-bottomed barges and manufactured caissons to create an artificial harbor. This harbor would support planned operations against Dutch coastal islands during the Great War. The Great War ended before the ambitious scheme could be properly tested in combat conditions. But Churchill never forgot the basic idea or its strategic potential. The concept remained alive in his restless mind through decades of political ups and downs. In the spring of 1942, weeks before the Dieppe catastrophe, Churchill attended a high-level conference where the seeming impossibility of capturing a port came up for detailed discussion. His response, recalled years later by multiple attendees, absolutely electrified everyone in that room. If we cannot capture a port through conventional assault, we shall construct one from scratch and take it with us across the Channel. The audacity of the statement left seasoned military professionals speechless. The engineering challenges seemed completely insurmountable to rational minds. How do you build a harbor capable of handling hundreds of cargo vessels simultaneously? How do you transport thousands of tons of concrete and steel components across open water in wartime conditions? How do you assemble such a massive structure under constant enemy artillery fire? How do you anchor it securely to the seabed in tidal waters that rise and fall 20 feet twice daily? How do you protect it from the violent storms that regularly plague the English Channel during certain seasons? Each fundamental question spawned dozens of additional technical problems. Each solution created new complications that required innovative engineering approaches. Yet the strategic necessity left absolutely no alternative course of action available. On May 30, 1942, Churchill issued a directive to Admiral Mountbatten that would set in motion the most ambitious construction project of the entire war. The directive, carefully preserved in War Office archives, consisted of exactly 60 words that changed military history forever. Piers for use on beaches. They must float up and down with the tide. The anchor problem must be mastered completely. Let me have the best solution worked out by competent engineers. Don't argue the matter endlessly. The difficulties will argue for themselves quite adequately. Mountbatten immediately assembled a team of Britain's finest engineers, naval architects, and construction specialists. The initial meetings took place at the Institution of Civil Engineers on Great George Street in Westminster. These sessions produced far more questions than practical answers. The sheer scale of what Churchill demanded seemed to violate fundamental laws of physics and engineering common sense. The project defied everything these professionals had learned during decades of harbor construction experience. Lieutenant General Frederick Morgan served as Chief of Staff to the Supreme Allied Commander. His Cossack planning team carefully calculated the minimum requirements for success. The artificial harbors would need handling capacity equivalent to the port of Dover. Dover ranked as Britain's busiest cross-channel harbor during peacetime operations. The artificial harbors must handle 12,000 tons of supplies daily regardless of weather conditions. They must safely accommodate ships ranging from small landing craft to Liberty ships displacing 10,000 tons. They must provide adequate shelter for vessels in seas up to force 6 on the Beaufort scale. Most critically, they must be completely assembled and fully operational within days of the initial invasion. The technical specifications alone filled hundreds of pages of detailed engineering documents. Every measurement had to be precise. Every calculation had to account for variables that might prove fatal if miscalculated. Civil engineer Hugh Ioris Hughes brought extensive experience in harbor construction to the project. This Welshman submitted detailed plans for a complete floating harbor to the Royal Navy between June and August 1942. His innovative design incorporated lessons learned from every major harbor project of the previous century. Other brilliant engineers contributed specialized components to solve specific technical challenges. Royal Engineer Lieutenant Alan Beckett designed flexible steel roadways that could rise and fall with the tides. These roadways would maintain continuous connection to the shore regardless of tidal conditions. Naval architects proposed using obsolete merchant ships as instant breakwaters. These vessels would be deliberately scuttled in predetermined positions to create protected water. The concept offered immediate availability and proven seaworthiness. The most ambitious element involved massive concrete caissons. These floating chambers could be towed across the channel behind tugboats. Once positioned correctly, they would be sunk to form permanent breakwaters against Atlantic storms. In October 1942, a combined operations conference received the code name Rattle. The meeting took place at Largs in Scotland, away from prying eyes and enemy intelligence networks. Commodore John Hughes Hallett and Royal Navy Captain Tom Hussey presented the complete scheme to assembled military planners. The presentation lasted 4 grueling hours and covered every technical aspect imaginable. Tidal calculations filled blackboards with complex mathematics. Concrete mixing ratios were debated with scientific precision. Wind-load factors were examined from multiple engineering perspectives. Skepticism dominated the initial reaction from seasoned military professionals. American officers serving on the planning staff expressed particular doubt about the feasibility. These men understood engineering challenges from years of practical experience. One U.S. Navy captain, whose name appears in the conference minutes only as Captain S., voiced the consensus concern with brutal honesty. "You're proposing to construct the equivalent of Dover Harbor from scratch. Dismantle it into thousands of individual pieces. transport those pieces across the most dangerous waterway in the world, reassemble them under enemy artillery fire, have the whole thing fully operational within 1 week. Gentlemen, I've been in the Navy for 25 years, and this is the most preposterous scheme I've ever encountered in military planning. The criticism was fair and based on solid professional judgment. Hughes Hallett's response, recorded verbatim in the conference transcript, demonstrated the desperate situation driving Allied planning efforts. "Captain, you're absolutely correct about every criticism you've raised. This scheme is completely preposterous by conventional standards. It defies every established principle of harbor engineering accumulated over centuries. It requires technical innovations that don't yet exist in practical form. It demands industrial production on a scale that may exceed our maximum national capacity. Yet I respectfully ask you to consider the only alternative available to us. We either solve these preposterous technical problems successfully, or we completely abandon any realistic hope of invading occupied Europe." The strategic choice really is that simple and that stark. A spontaneous demonstration helped convince the most stubborn skeptics in that room. Commander Robert Grant conducted an impromptu experiment using the conference room sink, paper model ships, and an ordinary hairbrush to simulate wave action. First, Grant placed the paper fleet directly in the sink and vigorously brushed the water's surface. The paper ships capsized immediately under the artificial wave action. The demonstration clearly showed unprotected vessels in rough water. Then Grant inflated a Mae West lifebelt and carefully placed it in the sink to represent a floating breakwater. The paper fleet sat inside the newly protected area. Again, he applied the brush with equal vigor, creating waves that broke harmlessly against the lifebelt barrier. The paper ships remained perfectly afloat despite the continued wave action. The demonstration was crude and almost childish in its simplicity. Yet it illustrated a fundamental truth that every naval officer understood instinctively. Protected water meant surviving ships under all conditions. Surviving ships meant sustained supply lines to shore. Sustained supply lines meant ultimate victory in the campaign. The logic was unassailable, despite the engineering challenges. The ambitious proposal traveled to Quebec in August 1943. Churchill and President Franklin D. Roosevelt met with the combined chiefs of staff to make final strategic decisions. Churchill presented the artificial harbor concept with his characteristic eloquence and persuasive power. His opening statement, carefully preserved in the conference minutes, captured the full audacity of the proposed plan. "Gentlemen, we propose to undertake the greatest construction project in military history. We will accomplish this in complete secrecy, at breakneck speed, under constant threat of enemy detection. We will build 2 complete harbors from scratch, using revolutionary engineering techniques. We will transport them across the channel in thousands of individual pieces. We will assemble them on hostile shores while under direct enemy fire. The Germans will not believe such a thing is remotely possible. Their complete disbelief will be our greatest strategic weapon." Roosevelt understood the concept immediately. His solid engineering background, dating back to his time as Assistant Secretary of the Navy, gave him genuine appreciation for the technical challenges involved. Yet he also grasped the absolute strategic necessity driving the proposal. The Joint Chiefs of Staff debated intensively for 2 full days. They examined every conceivable aspect of the plan with scientific precision. Concrete strength requirements were analyzed by structural engineers. Tidal predictions were verified by oceanographic experts. German coastal artillery ranges were calculated by ballistics specialists. Finally, on September 2, 1943, they issued their historic decision. The combined Chiefs of Staff estimate that the artificial ports will need to handle 12,000 tons per day, exclusive of motor transport, and function in all weather conditions. On September 4th, the official go-ahead was given to start work immediately on both harbors. Time was running desperately short. The invasion could not be delayed indefinitely while engineering problems were solved. Bitter infighting between the War Office and the Admiralty threatened to derail the entire project before construction could even begin. The Admiralty demanded complete control, arguing logically that anything floating fell under traditional naval jurisdiction. The War Office countered forcefully that harbor construction was fundamentally an Army engineering responsibility. Military engineers had built fortifications and harbors for centuries. This project simply represented a larger-scale version of familiar work. The bureaucratic dispute raged for 3 critical months. Countless planning meetings were consumed by jurisdictional arguments. Critical technical decisions were delayed, while departments fought for control. Only direct intervention by the Vice Chiefs of Staff ended the destructive conflict. On December 15, 1943, they imposed a practical solution by executive order. The Admiralty would manage the block ships to be scuttled as breakwaters. They would control the bombardons or floating outer breakwaters. They would supervise all assembly work on England's south coast. The Navy would also survey the French coast for suitable locations. They would mark navigation channels for safe passage. They would tow all components across the channel using their tugs and specialized vessels. The War Office would construct the concrete caissons codenamed Phoenix. They would build the floating roadways codenamed Whale. They would provide anti-aircraft protection for the construction sites and completed harbors. Once established in France, Army engineers would sink the caissons in precise positions. They would assemble the complete harbor according to predetermined plans. The division of labor finally established, actual construction could begin in earnest. The scale of the project completely dwarfed anything Britain had ever attempted during wartime. From the summer of 1943, construction proceeded with desperate urgency. Up to 45,000 personnel worked simultaneously across dozens of secret sites throughout southern England. The concrete caissons alone represented an absolute engineering marvel. The largest Phoenix units measured 200 feet in length, 60 feet in height, and weighed more than 6,000 tons when completely finished. A total of 213 caissons of various sizes would be required for both harbors. The concrete requirements consumed more than 1 million tons of reinforced concrete. Steel reinforcement demanded 70,000 tons of increasingly scarce wartime steel. These materials had to be diverted from other critical war production. Massive excavations were carved from the banks of the Thames and Medway rivers. These created the dry docks where Phoenix units could be constructed under controlled conditions. The construction process required precision that seemed impossible given the desperate urgency. Each caisson was essentially a floating concrete box with watertight integrity. It had to remain airtight except for controlled flooding valves. These valves would lower it to the seabed in precise, predetermined positions. The walls had to be thick enough to withstand violent Atlantic storms for months, yet they had to remain light enough to float during transport across the channel. Reinforcing steel had to be positioned with mathematical exactness to prevent catastrophic structural failure. Concrete had to be mixed, poured, and cured under controlled conditions. This happened despite chronic wartime shortages of cement and steel. Quality control could not be compromised despite time pressures. Commercial construction firms across Britain received lucrative contracts for individual caissons. Watty's Construction, Balfour Beatty, Henry Boot, Bovis and Company, Costain, John Lang and Son, Peter Lind and Company, Sir Robert McAlpine, Molem, Tarmac, and Taylor Woodrow all contributed sections. These firms worked in complete ignorance of the final purpose. Security absolutely demanded that construction workers know only their immediate task. The grand design remained secret even from those building it. Arthur Watts served as managing director of Watts Construction during the war years. He recalled decades later in a 1970 interview the atmosphere of mystery surrounding their work. Our workers built massive concrete pontoons according to specifications provided by government engineers. We had absolutely no idea what they were actually for. The rumor circulating among the men was that these were somehow related to post-war housing construction projects. When a senior officer from Whitehall visited our yards and saw how puzzled everyone looked, he reassured us that our work was vitally important for the war effort. Only after D-Day did we finally learn we'd been building sections of artificial harbors. The revelation amazed everyone who had worked on the project. The floating roadways presented equally daunting engineering challenges that pushed technology to its limits. Alan Beckett's revolutionary design called for steel bridge spans exactly 80 feet long. These were mounted on floating pontoons made of either steel or concrete components called beetles. The bridges had to be flexible enough to accommodate tidal variations of up to 20 feet, yet they had to remain rigid enough to support fully loaded trucks carrying critical supplies. The engineering tolerances were incredibly demanding. Beckett's solution involved a torsionally flexible joint system of remarkable ingenuity. This allowed each span to twist independently while maintaining continuous roadway surface. The mathematics of stress distribution required entirely new calculations. 16 kilometers of these whale roadways would be manufactured to exact specifications. Each section had to be precisely engineered to connect perfectly with its neighbors. No gaps or misalignments could be tolerated under operational conditions. The pierheads where ships would actually dock received the code name Spud. Each consisted of a massive pontoon with 4 adjustable legs that rested on the seabed. The pontoon floated up and down with the tides while maintaining constant position. Hydraulic systems allowed the legs to extend or retract as tidal conditions changed throughout each day. This maintained constant deck height relative to docked ships regardless of tide level. The engineering tolerances were measured in fractions of an inch, over structures weighing hundreds of tons. Comprehensive testing became absolutely crucial for success. The Scottish harbour at Garliston in Wigtownshire offered characteristics remarkably similar to the Normandy beaches. Flat, sandy bottom, moderate tidal range, remote location, and sparse population made it ideal. A complete security cordon was established around the entire test area. Local inhabitants were evacuated under wartime emergency powers without explanation. The whole area from Garliston through to the Isle of Withorn was declared completely off-limits to civilians. A military camp was hastily constructed at Cairnhead to accommodate hundreds of engineers and support workers. These personnel would test and refine the mulberry components under realistic conditions before the invasion. The extensive tests revealed numerous serious problems that would have proven catastrophic if discovered only on D-Day itself. Early floating roadway designs collapsed completely under the weight of a 7-ton truck when subjected to realistic wave action. Swiss roll-type flexible roads washed away entirely during a storm that hit the test site unexpectedly. Hip-on pontoons undermined in the sandy bottom, causing crocodile bridge spans to fail structurally under load. Only Beckett's whale designs survived the storm completely undamaged. This led directly to its adoption for the final harbor construction. The testing phase saved the entire project from potential disaster during the actual invasion. The massive floating breakwaters known as bombardons faced serious problems during testing. These enormous structures were built from steel and rubberized canvas. Engineers had to completely redesign them after early versions failed spectacularly. The first bombardment designs used hemp rope to connect individual units together. This seemed logical on paper. Hemp rope was strong and flexible. It could handle normal wave action without snapping. But testing revealed a fatal flaw. When storms hit, the ropes couldn't handle the strain. They parted under extreme conditions. The massive bombardment units broke free from each other. They drifted toward the inner harbor areas. If this happened during actual operations, the results would be catastrophic. Loose bombardons could crush ships. They could destroy pier structures. They could wreck entire harbor sections. Engineers went back to the drawing board. They replaced all hemp rope connections with steel cables. These new cables were much stronger. They also added backup safety systems. If one cable failed, others would hold. Multiple tests confirmed the new design worked better. Steel cables could handle storm forces that destroyed hemp ropes. The backup systems provided extra security. Engineers felt confident the bombardons would hold together. Security around the Mulberry project reached extreme levels. Officials treated every detail as top secret. Even the project code name was chosen for maximum secrecy. The name Mulberry revealed absolutely nothing about the project's true purpose. It was simply the next available designation on a long list. This list contained hundreds of randomly selected code names. Each new project got the next name in sequence. All written communications used only the Mulberry code name. Documents never mentioned artificial harbors. They never referenced floating ports. Workers had no idea what they were really building. Every person working at construction sites signed the Official Secrets Act. This legal document made leaking information a serious crime. Violators faced imprisonment or worse. The threat kept most workers quiet. Photography was strictly forbidden at all Mulberry sites. Guards confiscated cameras from anyone approaching work areas. Film was destroyed immediately. Even sketches or drawings could land someone in prison. Intelligence services monitored pubs near construction yards. Agents listened for loose talk about the mysterious project. Workers sometimes drank too much and started talking. These conversations were carefully recorded and analyzed. German aerial reconnaissance posed a constant threat to security. Luftwaffe planes photographed southern England on a regular schedule. They searched for signs of invasion preparations. Any unusual construction activity drew special attention. The Phoenix caissons created the biggest security headache. These massive concrete structures were simply too large to hide. Once construction began, German spy planes would certainly spot them. A clever cover story provided the solution. Officials claimed the Phoenix units were experimental anti-submarine barriers. They would supposedly be deployed in the English Channel to stop U-boats. This explanation sounded plausible to German intelligence analysts. Britain desperately needed better anti-submarine defenses. The cover story apparently worked. German forces made no special preparations to counter artificial harbors. An extraordinary security breach nearly exposed the entire Mulberry project in May 1944. The Daily Telegraph crossword puzzle began including highly classified words. These words were directly related to Operation Overlord. On consecutive days, crossword clues led to solutions that were invasion beach code names. Utah appeared as an answer. So did Omaha, Juneau, Sword, and Gold. These were the 5 designated invasion beaches. Most alarmingly, Mulberry itself appeared as a crossword solution. This was the project's top secret code name. Its appearance in a public newspaper sent security officials into panic mode. MI5 immediately investigated Leonard Daw. He was the headmaster who compiled the Telegraph crossword puzzles. Intensive interrogation followed. Investigators suspected Daw might be a German agent. The investigation revealed an innocent explanation. Daw often asked his students for interesting words to include in puzzles. Many of these students lived near American military barracks. Overlord planning was underway at these facilities. Classified words entered Daw's vocabulary through casual conversations. Students overheard military personnel talking. They repeated interesting words to their teacher. Daw used them in crosswords without knowing their significance. MI5 concluded the security breach was indeed coincidence, but it was an extremely unnerving coincidence. The investigation continued until after D-Day. Officials wanted absolute certainty that Daw wasn't using an impossibly subtle communication method. By June 1944, the artificial harbors existed as thousands of separate components. These pieces were scattered across southern England at various assembly points. The logistics of moving them seemed almost impossible. First, components had to reach assembly points from construction sites. Then they had to cross the English Channel. Finally, they needed positioning off the Norman coast. The scale boggled even experienced military planners. 2 complete harbors had been constructed with meticulous attention to detail. Mulberry A would support American forces at Omaha Beach. This location was near the town of Saint-Laurent-sur-Mer. Mulberry B carried the honorary name Port Winston. This honored Churchill's crucial support for the project. Port Winston would support British and Canadian forces at Gold Beach near Arromanches. Each harbor required staggering amounts of materials. Approximately 600,000 tons of concrete and prefabricated steel went into every harbor. The components included precise numbers of specialized units. 213 Phoenix caissons of various sizes formed the main breakwaters. 10 miles of whale floating roadways would connect ships to shore. 33 pierheads provided docking facilities for multiple vessels simultaneously. 70 obsolete merchant ships would be deliberately scuttled as additional breakwaters. Their positions received the code name Gooseberries. 24 massive bombardon floating breakwaters provided outer protection against Atlantic swells. Moving this artificial fleet required extraordinary naval resources. 150 ocean-going tugs were specially modified for long-distance towing operations. These vessels were distinguished by large M letters painted on their funnels. Crews took fierce pride in their special assignment. They understood they were participating in history's most ambitious engineering project. The towing operations alone presented staggering complexity that tested every skill. Phoenix caissons had to be towed at speeds not exceeding 4 knots. Higher speeds could cause structural damage to the concrete structures. The journey from English assembly points to the Normandy coast would take 2 full days under ideal conditions. Weather predictions became absolutely crucial for success. Rough seas could damage delicate components during the crossing. Storm conditions could part tow cables and send caissons drifting. The tugs had to navigate mine-infested waters while maintaining precise station in massive convoys. Royal Navy minesweepers worked continuously ahead of the Mulberry convoys. They cleared safe lanes through defensive minefields laid months earlier. German U-boats had planted thousands of mines across likely invasion routes. June 4, 1944, brought the first movement orders for the artificial harbors. Sections of both Mulberry harbors began moving behind their assigned tugs. They were positioned in the middle of the English Channel, waiting for the invasion originally scheduled for June 5th. Then, weather conditions forced a dramatic change of plans. A massive storm system swept across the channel from the Atlantic. High winds and rough seas made invasion impossible. Eisenhower reluctantly ordered a 24-hour postponement. The Mulberry components wallowed in rough seas while Supreme Commander agonized over whether to proceed. Another postponement could push the invasion back weeks. Tidal conditions and moon phases wouldn't be favorable again until late June. When Eisenhower finally gave the order to launch Overlord on June 6th, the artificial harbor components were already at sea. They had been riding at anchor in the Channel for over 24 hours. In the pre-dawn hours of D-Day, Allied soldiers stormed ashore under withering German fire. Simultaneously, the first elements of the Mulberry harbors were being towed into their final positions. The operation proceeded with choreographed precision despite the chaos surrounding the largest amphibious assault in military history. On D+1, June 7th, the first Phoenix caissons moved into position about 1 mile offshore from both Omaha and Gold Beaches. Powerful harbor tugs maneuvered the massive concrete structures with remarkable precision and delicacy. The tugs nudged each caisson into exact positions marked by buoys. Royal Navy survey ships had laid these navigation markers days earlier. The positioning had to be perfect for the harbor design to function properly. The controlled flooding of Phoenix caissons demonstrated brilliant engineering design. Each caisson contained multiple watertight chambers with individual flood valves. Engineers could flood specific chambers to achieve exact positioning and orientation. This process allowed precise control over how each caisson settled to the seabed. The work required hours of careful adjustment for each individual structure. But the results more than justified the painstaking effort involved. As the Phoenix breakwater took shape, it created sheltered water where ships could anchor safely. The protection from Atlantic swells was immediately apparent. Ships that would have been tossed around in open water rode peacefully at anchor. Simultaneously, 70 obsolete merchant ships moved into position for their final voyage. These vessels carried the code name Corn Cobs. Collectively, they would create the gooseberry breakwaters around each harbor. The ships had been assembled months earlier at Oban on Scotland's west coast. Every valuable item had been stripped from their hulls. They were ballasted for precise buoyancy characteristics. Scuttling charges were fitted in predetermined locations. These vessels made their final voyage under their own steam power. Crews navigated to predetermined coordinates off the invasion beaches. At exactly the right moment, they opened seacocks and detonated the scuttling charges. The crews abandoned ship as the vessels settled to the bottom. Each ship sank in its carefully planned position. This created an outer line of protection against Atlantic swells and enemy attack. At Utah Beach, 10 ships went down in perfect formation. The vessels included the Benjamin Conti, David O. Saylor, George S. Wasson, and Vitruvius. Each name represented a ship that had served faithfully before making this final sacrifice. At Omaha Beach, another formation of corncobs established the outer perimeter of Mulberry A. The scuttling operations proceeded so smoothly that most ships settled within 50 feet of their assigned positions. This represented a remarkable achievement in naval precision. Deliberately sinking a ship exactly where intended required extraordinary skill. Wind, current, and tide all affected where a vessel would finally rest on the bottom. The whale roadways came next in the carefully orchestrated sequence. Long trains of linked pontoons and bridge spans snaked across the channel. Dedicated tugboats towed these flexible structures behind them. Once in position offshore, Royal Engineers secured the roadways to the spud pierheads. These pierheads were driven deep into the seabed. They provided stable anchor points that could handle the enormous stresses. The roadways then extended toward shore in graceful curves. The flexible joints that Beckett had designed proved their worth immediately. The roadways undulated with the waves while maintaining complete structural integrity. By June 13th, just 1 week after D-Day, Mulberry B at Arromanches had developed sufficiently to provide 2 crescent-shaped harbors. These harbors could accommodate up to 75 Liberty ships and smaller craft simultaneously. The speed of construction astonished even the engineers who had planned every detail. Within just 7 days of the D-Day landings, both artificial harbors were beginning to handle cargo operations. The first supply ships to use the Mulberry facilities found themselves in a surreal situation. They were docking at piers that hadn't existed 10 days earlier. These harbors were built from materials that had been scattered across England just 2 weeks before. Ship captains accustomed to traditional stone and steel harbors marveled at the floating structures. Everything rose and fell with the tide, yet remained perfectly functional throughout the tidal cycle. Captain James Morrison of the Liberty ship, Robert E. Peary, wrote detailed observations in his ship's log. Approached what the charts show as open beach. Instead, found complete harbor facilities, including floating piers, breakwaters, and navigational markers. Docked at Pier 7 of Arromanches Harbor and discharged 400 tons of ammunition, 200 tons of rations, and 150 vehicles in 8 hours. The entire facility floats on the tide, rising and falling 15 feet between high and low water. Yet it remains perfectly functional throughout the tidal cycle. The engineering involved defies my comprehension. These British have created harbors from thin air. Then disaster struck with devastating suddenness. On June 19, 1944, the worst June storm in 40 years descended on the English Channel. Weather forecasters had failed to predict its severity. For 3 brutal days, northeasterly winds of force 6 to force 8 pounded the Normandy coast. Waves reaching 8 feet in height crashed against the artificial harbors with relentless fury. The Bombarden outer breakwaters had been designed to absorb exactly this type of punishment. But the storm exceeded all design specifications. Some Bombardens broke apart completely under the wave assault. Others tore free from their heavy anchor chains and drifted into the inner harbors. There they smashed into Phoenix caissons and whale roadways like battering rams. The damage spread rapidly as loose components created chain reactions. At Omaha Beach, Mulberry A suffered catastrophic damage that would prove irreparable. The American harbor had not been fully completed when the storm arrived. Critical reinforcement and anchor systems were still being installed. Phoenix caissons cracked under the relentless wave assault. Concrete structures that had seemed indestructible proved vulnerable to sustained pounding. Whale roadways broke free from their moorings and washed onto the beach in tangled wreckage. By the time the storm finally abated on June 22nd, Mulberry A was beyond any hope of repair. Surveys showed the harbor looked like a battlefield. Broken concrete and twisted steel littered the seabed. The American decision to abandon Mulberry A came quickly after damage assessments were completed. Engineering surveys showed that restoring the harbor would take longer than building it originally. Damaged components would first need to be removed before reconstruction could begin. Instead, the Americans made a pragmatic decision. They salvaged every usable section from Mulberry A. These components were sent to reinforce Mulberry B at Arromanches. The British harbor had been more protected by the natural geography of Gold Beach. It had also been more completely assembled before the storm struck. Mulberry B survived with significant damage, but remained fundamentally functional. Substantial reinforcement followed using units salvaged from the American harbor. The Phoenix caissons were pumped full of sand to give them much greater stability. This measure undoubtedly explained the extended service life of the British port. The storm validated the Mulberry concept even as it destroyed one of the harbors. At Omaha Beach, where Mulberry A lay in ruins, The Gooseberry breakwater had held firm throughout the three-day battering. Ships anchoring in the protected water behind the scuttled block ships rode out the storm with minimal damage. Without even this basic protection, the June storm would have scattered the entire invasion fleet. The potential consequences could have doomed the entire Normandy operation. Hundreds of ships might have been driven onto the beaches or out to sea. The invasion could have failed at its most critical moment. Lieutenant Colonel George Shalleck commanded 20 Port Group Royal Engineers. His unit was responsible for operating Mulberry Bee throughout its service life. He wrote detailed after-action reports that captured the storm's impact. The storm of June 19 to 22 subjected our harbor to conditions far exceeding design specifications. That any portion survived testifies to the quality of British engineering and the foresight of our planners. The bombardons which failed did so while absorbing punishment that would have destroyed the entire invasion fleet. Had those ships been exposed to open water, the casualties would have been catastrophic. Even in failure, the Mulberry concept proved its fundamental value to the success of Operation Overlord. The loss of Mulberry A forced American forces to rely entirely on direct beach landing of supplies. This technique had been practiced but never tested on such a massive scale. American beachmasters refined their procedures to unexpected levels of efficiency. By early July, Omaha Beach was handling 12,000 tons of supplies daily despite lacking a proper harbor. This achievement surprised everyone, including the original planners. Yet even this impressive success depended heavily on the Gooseberry breakwater. The scuttled ships provided essential protection from Atlantic swells. Without them, direct beach landing would have been impossible during rough weather. Mulberry Bee at Arromanches continued operating far beyond its original design life. The harbor had been intended to function for just 3 months. This would provide sufficient time to capture and restore the major port of Cherbourg. Instead, Port Winston remained operational for 10 full months after D-Day. The statistics of what this single artificial harbor accomplished defied all expectations and beliefs. Through Port Winston passed 2.5 million men, 500,000 vehicles, and 4 million tons of supplies. At peak efficiency, the harbor was landing 7,000 tons of equipment and supplies every single day. The port operated around the clock, with ships docking at any hour. Day and night, vessels discharged their cargo onto the floating piers. The Whale roadways proved their worth far beyond anyone's most optimistic expectations. Designed for a 3-month operational lifespan, they handled constant heavy traffic for 10 months. Fully loaded trucks drove directly from Liberty ships anchored offshore onto French soil. The route crossed floating bridges that rose and fell with each tide. Many of these bridge spans found second lives after the war ended. They were repaired and used to replace bombed bridges across France, Belgium, and the Netherlands. Examples remain visible today as permanent monuments. One span crosses the Orne River in Normandy. Another bridge spans the Moselle River between Cattenom and Koenigsmacher. These wartime bridges still carry civilian traffic more than 75 years later. The German reaction to the Mulberry harbors revealed the complete failure of their military intelligence services. It also exposed fundamental flaws in their strategic thinking about the invasion. German commanders had based their entire defensive strategy on one critical assumption. They believed the Allies would absolutely need to capture a major port facility. This assumption shaped every aspect of German defensive planning. Rommel had fortified Cherbourg, Le Havre, and other harbors with massive concrete defenses. He positioned troops and artillery specifically to defend these port facilities. The Atlantic Wall contained millions of mines and thousands of bunkers concentrated around harbor approaches. When Allied forces came ashore on beaches rather than attacking ports directly, German intelligence initially misinterpreted the landings. They assumed this was evidence of a limited diversionary raid rather than the main invasion force. Even when the enormous scale of the D-Day landings became apparent, German commanders still expected Allied forces to move rapidly toward Cherbourg. They positioned their reserves accordingly. The appearance of artificial harbors off the invasion beaches shocked the German high command completely. They had received no intelligence warning of the Mulberry Project despite its massive scope and thousands of workers. The concept violated every German assumption about what was militarily possible. Mobile harbors seemed like science fiction rather than military reality. Their disbelief bought the Allies precious time to consolidate the beachhead. Albert Speer provided the most eloquent testament to the Mulberry Harbor's strategic impact. As Nazi Germany's Minister of Armaments and War Production, he understood industrial warfare better than most German officials. After the war, during Allied interrogation, and later in his published memoirs, Speer reflected on the Atlantic Wall's complete failure. His words captured the essence of why Germany ultimately lost the war. To construct our Atlantic defenses in 2 years, we used 17 million cubic meters of concrete and 1.2 million tons of steel. A fortnight after the enemy landings, this costly effort was brought to naught by an idea of simple genius. The simple genius Speer referenced was the revolutionary Mulberry concept. Germany had invested enormous resources into fortifying every significant port along the Atlantic coast from Norway to Spain. Nazi military planners believed these fortifications made successful invasion impossible without catastrophic Allied casualties. The defenses were designed to make capturing ports cost-prohibitive. Instead, the Allies simply bypassed all the fortified ports entirely. They brought their own harbors with them across the English Channel. This represented much more than a clever tactical surprise. It demonstrated a fundamental difference in how the opposing sides approached modern warfare. German military thinking remained rooted in 19th-century concepts of fortress warfare and static defense of strongpoints. The Allies embraced innovation and creative problem-solving. They were willing to attempt solutions that conventional military wisdom deemed completely impossible or impractical. This contrast extended far beyond the Mulberry Harbors to encompass Allied strategy as a whole. While Germany relied on static defenses and counterattacks with armored reserves, the Allies developed specialized equipment to overcome every type of obstacle. Hobart's funnies epitomize this innovative approach to military engineering. This collection of modified tanks included flail tanks for clearing minefields, bridge-laying tanks for crossing obstacles, and amphibious tanks for swimming ashore. Germany certainly possessed technical brilliance. Their weapons included revolutionary designs like the V-2 rocket and jet aircraft, but they lacked the industrial capacity and strategic flexibility to turn technical innovations into war-winning advantages. The Allies, particularly the United States and Britain working in close cooperation, successfully combined innovation with massive industrial production capability. The Mulberry Harbors perfectly exemplified this winning combination. The engineering innovations were cutting-edge by any standard. Beckett's flexible roadway joints represented breakthrough design. The Phoenix Caisson's controlled flooding systems were revolutionary. These technical achievements matched anything German engineers produced. Yet the Mulberry Project succeeded because British industry could manufacture these innovations in enormous quantities. This production occurred despite 4 years of total war and severe material shortages. Over 45,000 workers contributed simultaneously to Mulberry construction across dozens of sites. Commercial firms throughout Britain diverted resources from other essential war work to produce specialized components. The scale of coordination required unprecedented cooperation. Dozens of government ministries worked together smoothly. Multiple military services coordinated their efforts seamlessly. Private companies shared resources and expertise freely. This organizational achievement matched and perhaps exceeded the technical accomplishment. Modern project management concepts were decades in the future, yet the Mulberry Project succeeded through effective coordination. Consider the Phoenix caissons alone as an example of organizational complexity. Building 213 massive reinforced concrete structures required more concrete than most entire nations produced annually. Construction sites had to be created from scratch along riverbanks throughout England. Raw materials, including cement, steel, and aggregates, had to be allocated despite desperate wartime shortages. Transportation to assembly points required specialized equipment and extremely careful scheduling. Quality control procedures had to ensure every caisson could survive ocean towing and potential storm conditions. The cross-channel towing operation deserves recognition as a remarkable maritime achievement. Moving 600,000 tons of concrete and steel across 30 miles of potentially hostile water stretched naval capabilities to their absolute limits. The 150 tugs involved in Operation Mulberry represented a significant portion of Britain's entire tugboat fleet. Many were commercial vessels pressed into military service for this special mission. Crews received only minimal training on towing oversized loads through minefields and enemy-controlled waters. Yet the loss rate during cross-channel operations remained remarkably and surprisingly low. Only a handful of Phoenix caissons were actually lost during transport operations. Most of those were damaged during the June 19th storm, rather than during the actual channel crossing itself. Rest had become almost impossible to find. The date etched in every mind was May 20th, 1944. Around them, final preparations moved forward with desperate urgency. What they had managed to construct defied every rational expectation. 3 years earlier, if anyone had dared suggest such an audacious plan, the response would have been immediate dismissal. The very concept would have seemed like pure fantasy. Yet here they stood, surrounded by proof that fantasy had transformed into approaching reality. The weight of potential failure pressed down on everyone involved. If this massive undertaking collapsed, the consequences would be catastrophic beyond imagination. Personal testimonies from Royal Engineers who later operated the Mulberry installations in France offer invaluable insights into what they had achieved. These ground-level accounts reveal the true magnitude of their accomplishment. Sapper William Hutchinson had been assigned to the 20th Port Group. His letters home to family members in July 1944 painted vivid pictures of daily life at the artificial harbor. His words carried the exhaustion and amazement that defined their experience. Work days stretched to 18 grinding hours just to keep Port Winston functioning properly. The massive harbor structure seemed alive somehow. It possessed an almost organic quality that fascinated and unnerved them. Every single tide brought dramatic changes that demanded constant attention. The entire floating installation would rise a full 15 feet with incoming water. Then it would settle back down as the tide retreated. This endless cycle created enormous stresses on every component. Nothing could remain static in such an environment. Teams worked around the clock making essential adjustments. Moorings required constant inspection and retightening. Pontoon sections needed regular examination for stress fractures and damage. Roadway segments suffered continuous wear from heavy traffic and had to be repaired immediately. Ships arriving at pierheads needed careful guidance through the complex harbor layout. German artillery positions inland sent shells screaming toward them at irregular intervals. The enemy gunners had calculated the range precisely. Every explosion sent shock waves through the water and rattled the floating structures. Luftwaffe bomber raids arrived with predictable regularity each night. The drone of approaching engines created tension that never fully disappeared. Despite these constant threats and challenges, supply operations continued without interruption. The flow of essential materials never stopped. On particularly busy days, 40 ships would arrive carrying everything an advancing army required. Tanks rolled off transport vessels onto the floating roadways. Ammunition moved in steady streams toward shore. Food rations filled countless trucks. Fuel tankers discharged thousands of gallons. Medical supplies reached field hospitals without delay. The realization that struck everyone was almost impossible to process. This entire port facility had not existed just 1 month earlier. They had assembled every component under direct enemy fire. Parts had been manufactured in Britain, transported across dangerous waters, and fitted together like pieces of an enormous puzzle. The scope of what they had accomplished seemed to exceed human capability. Merchant Navy crews delivering vital supplies through Port Winston expressed constant amazement at what they encountered. Their expectations had been shaped by decades of experience at conventional harbors. What they found challenged everything they thought they understood about maritime operations. Captain Robert Fraser commanded the Liberty ship John P. Holland. His vessel had made multiple voyages to Arromanches, carrying essential cargo. After his third delivery run, he filed a detailed report with his shipping company. His observations captured the profound impact of the artificial harbor on maritime operations. Standard procedure for unimproved coastlines involved anchoring offshore and transferring cargo to smaller craft. These lighter vessels would then ferry supplies to the beach in multiple trips. The process was slow, dangerous, and highly dependent on weather conditions. Fraser had expected exactly this type of challenging operation. Instead, radio communications directed him to proceed directly to Pier 11 within Port Winston. The instructions seemed almost routine, as if he were approaching any established commercial harbor. What he discovered upon arrival defied his professional experience entirely. The complete harbor facility spread before him like a permanent installation that had existed for decades. Massive breakwaters protected an inner harbor from channel storms. Floating piers extended far enough into deep water for ocean-going vessels to dock directly. Navigational aids marked safe passages with the precision found at major ports worldwide. Everything appeared as substantial and reliable as facilities he had used throughout 20 years of maritime service. The engineering expertise required to create such a complex installation from nothing seemed almost supernatural. The technical challenges of anchoring floating structures against powerful channel tides and storms would have daunted the most experienced harbor designers. Most remarkable of all was that this entire facility continued operating efficiently under active combat conditions. German artillery shells fell sporadically throughout the harbor area. Luftwaffe attacks came nightly. Yet cargo operations proceeded with clockwork precision, despite these deadly interruptions. His ship discharged 500 tons of critical supplies in just 6 hours. The efficiency matched or exceeded what they achieved at established peacetime ports operating under ideal conditions. As soon as unloading completed, harbor control directed them to depart immediately. Another vessel was already approaching to take their berth. The turnover rate impressed even veteran merchant mariners. The strategic importance of these artificial harbors to the entire Normandy campaign cannot be exaggerated. Without them, Allied commanders would have faced 3 equally terrible alternatives. Each option carried consequences that could have doomed the entire invasion. The first possibility involved accepting massive casualties to capture a heavily fortified port like Cherbourg immediately after the initial landing. This would have required committing major forces when they were weakest and German resistance was strongest. The assault would have been extraordinarily costly in human lives with no guarantee of success. The second alternative meant relying completely on beach landings for all supply operations. This approach would have exposed the entire invasion fleet to weather conditions that could destroy everything they had worked to achieve. The devastating June storm that actually occurred demonstrated exactly how vulnerable beach operations remained to natural forces. The third option involved delaying the invasion indefinitely while searching for alternative solutions that might not exist. This postponement could have allowed German forces time to strengthen their defenses further. It might have given enemy commanders opportunities to relocate reserves and concentrate them against likely landing sites. The Mulberry solution eliminated all these impossible choices completely. It provided Allied forces with harbor capacity equivalent to any major commercial port. This was achieved without the terrible casualties that would have resulted from direct assault. It removed the dangerous vulnerability that came with dependence on open beach operations. The artificial harbors handled sufficient cargo tonnage to sustain the massive buildup of forces required in Normandy during those critical first months. Supply lines remained secure and reliable despite enemy attempts to disrupt them. The harbor installations proved their worth repeatedly under the most demanding conditions imaginable. By June 26, 1944, when Cherbourg finally fell to advancing American forces, the immediate strategic crisis had passed. Allied troops had established an unshakable foothold on French soil. Even when German demolition experts left Cherbourg's port facilities completely unusable for many weeks, the advance continued without significant interruption. Port Winston maintained steady supply flow throughout this crucial period. The strategic implications of successful artificial harbor operations extended far beyond the Normandy campaign itself. The achievement fundamentally altered Allied thinking about amphibious warfare doctrine. Military planners no longer assumed they needed to capture existing ports immediately after any landing. Future amphibious operations could target any suitable beach area with confidence. Artificial harbor technology could sustain major operations until permanent port facilities were captured and restored to working condition. This flexibility provided Allied commanders with enormous advantages when selecting landing sites for subsequent invasions. Beach selection could now be based primarily on defensive vulnerability rather than proximity to existing harbors. This freedom transformed strategic planning completely. German commanders could no longer concentrate their defensive efforts around major ports with confidence that Allied forces would be forced to attack them. The psychological impact on German defensive planning was profound. They faced the terrifying prospect that Allied forces might land anywhere along thousands of miles of heavily fortified coastline. This uncertainty forced Germany to spread defensive forces much more thinly than they preferred. Resources that could have been concentrated at decisive points were instead scattered across vast areas. Military planners had already begun drawing detailed plans for using Mulberry technology in the eventual invasion of Japan. Engineers were dispatched to the Pacific Theater to survey potential landing beaches and assess construction requirements for artificial harbors in that region. The atomic bombs dropped on Hiroshima and Nagasaki in August 1945 made these elaborate preparations unnecessary. However, the planning effort demonstrated how completely the Mulberry concept had been embraced as standard Allied amphibious procedure. No comparable wartime engineering achievement has been attempted since 1944. The unique combination of technical innovation, massive industrial production, absolute security requirements, complex logistics coordination, and operational deployment under direct enemy fire has never been replicated. Modern military forces studying amphibious warfare continue to examine the Mulberry Harbors as the definitive case study in solving seemingly impossible problems through pure engineering ingenuity. Physical remnants of Port Winston can still be observed today at Arromanches. Phoenix caissons remain visible during low tide periods, marking the location of the outer breakwater that once protected the artificial harbor from channel storms. Local fishing boat captains use these concrete monuments as navigation landmarks when approaching the coastline. Tourists visiting the historic D-Day beaches can see concrete evidence of what Allied engineers accomplished during those desperate months in 1944. The massive structures serve as permanent reminders of human determination and technical innovation under the most challenging circumstances imaginable. Several Phoenix caissons also dot the British coastline, serving as unintended monuments to construction problems and testing failures that occurred during the development process. At Pagham Harbour in West Sussex, a caisson known as the Near Mulberry suffered structural failure during the towing process and could not be refloated successfully. This massive concrete structure remains visible during low tide periods. It has been designated as a protected historic monument, officially recognizing its significance to the wartime engineering effort. Another caisson, called the Far Mulberry, suffered catastrophic structural damage when its back broke during a violent storm the night before D-Day itself. This damaged structure lies in deeper water offshore from Pagham Harbour. While not easily accessible to casual visitors, it represents the enormous risks involved in the entire Mulberry project. At Thorpe Bay near Southend-on-Sea, another Phoenix unit being towed from Immingham to Southsea began taking on water through stress fractures in its hull. Rather than risk losing the entire structure in deep water, tugboat crews intentionally beached the damaged caisson on a sandbank in the Thames estuary. This structure has also achieved scheduled monument status with English heritage. Visitors willing to wade through Thames estuary mud during low tide can examine its construction details firsthand. These accidental monuments serve as important reminders that the Mulberry project involved enormous technical risks throughout its development and deployment. Not every component performed exactly as engineers had designed and calculated. Not every caisson reached French waters intact and ready for installation. The devastating June storm destroyed Mulberry A completely and caused severe damage to Port Winston. Yet the overall project succeeded brilliantly because British and American engineers had built extensive redundancy into every critical system. They had developed multiple solutions for each major technical problem. Most importantly, they demonstrated remarkable ability to adapt quickly when initial designs failed to perform as expected under actual operating conditions. The long-term impact of Mulberry Harbour innovations on civilian engineering practices deserves much greater recognition than it has received. Technical advances developed under urgent military necessity found important peacetime applications in the post-war period. These innovations influenced construction practices for decades after 1945. Floating bridge technology advanced significantly thanks to Alan Beckett's revolutionary whale roadway design. The principles he developed for creating flexible yet stable floating roadways influenced bridge construction projects worldwide. Post-war harbor construction incorporated crucial lessons learned about breakwater design and accommodation of extreme tidal variations. Concrete mixing and curing techniques that had been developed to produce Phoenix caissons under severe wartime pressure and material shortages improved commercial construction practices substantially. Quality control methods pioneered during Mulberry construction became standard industry procedures for major projects. Perhaps most significantly, The entire Mulberry Project demonstrated conclusively that massive engineering undertakings could be completed in months rather than years, when genuine urgency demanded rapid results. Traditional construction timeframes were based on peacetime conditions with normal resource availability and conventional management approaches. The organizational skills, detailed planning methods, and innovative execution techniques developed during artificial harbor construction influenced major infrastructure projects around the world throughout the post-war period. Personnel who had gained experience managing complex technical projects under severe constraints dispersed into commercial construction after 1945. They brought with them hard-won expertise in coordinating multiple contractors, managing scarce resources, and maintaining quality standards under extreme pressure. Public recognition of the Mulberry engineers' achievements came disappointingly slowly. Wartime security classifications kept technical details secret for many years after Germany's surrender in 1945. The engineers themselves, modest by professional training and personal inclination, rarely sought public attention or acclaim for their contributions. Ove Arup's extensive technical archives remained privately held until his family donated them to McMaster University in 1976. Hugh Ioris Hughes received no significant public honors during his lifetime, despite his fundamental contributions to harbor design and construction management. Alan Beckett, whose whale roadway innovations proved absolutely crucial to Mulberry's success, continued his distinguished engineering career in relative obscurity for decades. Only when military historians began examining wartime technical achievements in detail did the true scale of the artificial harbor accomplishment begin receiving appropriate recognition. The institution of civil engineers included the Mulberry Harbors among 200 significant projects celebrated during their bicentennial anniversary celebrations in 2018. Scholarly studies have examined both technical and organizational aspects of the project with increasing sophistication. Television documentaries have brought the remarkable story to much wider public audiences. Military historians now acknowledge that D-Day's ultimate success depended as much on engineering innovation as on battlefield courage and tactical brilliance. The fundamental contrast between Allied and German approaches to the invasion challenge crystallized perfectly in their different responses to the harbor problem. Germany chose what appeared to be the obvious and logical solution. They decided to fortify existing ports so heavily that capture would become impossible for any attacking force. The Atlantic Wall, consuming millions of tons of concrete and incorporating elaborate defensive systems, represented conventional military thinking applied with characteristic German thoroughness and engineering expertise. Every major port from Norway to Spain bristled with artillery batteries, machine gun nests, minefields, and underwater obstacles designed to destroy any invasion fleet. The Allies chose what appeared to be a completely impossible alternative solution. They decided to make existing ports irrelevant by creating entirely new harbors wherever they were strategically needed. This radical approach required absolute faith that impossible engineering challenges could be overcome through innovation and massive industrial effort. It required senior military and political leaders willing to authorize enormous expenditures on completely unproven technical concepts. It demanded engineers willing to attempt projects that their professional training indicated couldn't be accomplished successfully. It needed construction workers laboring in ignorance to build mysterious components they didn't understand for purposes they couldn't imagine. This fundamental difference in strategic mindset explains much about why the Allies ultimately won the war. German military culture emphasized obedience to authority, rigid hierarchical command structures, and strict adherence to proven methods that had succeeded in previous conflicts. This approach produced extraordinary excellence in tactical execution, but dangerous inflexibility in strategic planning. When Allied actions violated basic German assumptions about how warfare should be conducted, their command structure struggled desperately to adapt to changing circumstances. Allied military culture, particularly the unique Anglo-American cooperation that developed during the war, placed much greater emphasis on innovation, tactical flexibility, and pragmatic problem-solving approaches. This cultural orientation sometimes produced apparent chaos and frustrating inefficiency in day-to-day operations. However, it enabled remarkably rapid adaptation to unexpected circumstances and creative solutions to unprecedented challenges. When conventional military solutions proved completely inadequate, Allied commanders actively sought unconventional alternatives that might change the strategic equation entirely. The Mulberry Harbors embodied this crucial cultural difference in the most dramatic way possible. A German general confronted with the harbor supply problem would have calculated the forces required to capture Cherbourg through direct assault and accepted the inevitable casualties as necessary for strategic success. An Allied general authorized building floating cities from scratch to bypass the entire problem through technical innovation. On June 6, 1984, exactly 40 years after D-Day, a group of surviving Mulberry engineers gathered at Arromanches to reflect on their extraordinary wartime achievement. The emotional reunion brought together British and American participants, military personnel, and civilian contractors, original designers and construction workers who had built the components. Their personal reminiscences, carefully recorded by Imperial War Museum historians, provide a fitting conclusion to the remarkable Mulberry story. Bruce White, who had supervised much of the actual harbor construction, spoke at the reunion dinner with obvious emotion. His words captured the feelings shared by everyone who had participated in the project 4 decades earlier. They had been young men facing what appeared to be an absolutely impossible technical challenge: build a complete harbor facility that could be assembled in mere days rather than years, create structures that could float yet withstand the worst Atlantic storms, design installations that could handle more cargo tonnage than Dover while being anchored to sand rather than solid bedrock. Every engineering principle they had learned during their professional education insisted such requirements couldn't be met simultaneously. The technical challenges appeared to violate fundamental laws of physics and structural engineering, yet they had no choice but to attempt the impossible. The success of the entire invasion depended completely on solving these unprecedented problems. So they stopped thinking about all the reasons why their assignment couldn't work and focused entirely on making it work somehow. They tested innovative designs, experienced failures, modified their approaches, and tested again. They manufactured harbor components on a scale that strained Britain's entire industrial capacity to its absolute limits. They towed massive floating concrete structures across mine-infested waters under constant threat of enemy attack. They assembled complex harbor installations while German artillery shells exploded around them and Luftwaffe bombers attacked overhead. The final result worked, though not perfectly according to original specifications. They lost Mulberry A completely during the devastating June storm. Many individual components failed under operational stresses and had to be replaced or extensively repaired. Constant maintenance was required to keep the installations functioning properly. But the artificial harbors worked well enough to accomplish their strategic mission. Port Winston maintained steady supply flow throughout the critical period. The harbor installations bought precious time needed to capture and repair Cherbourg. That time made the crucial difference between ultimate victory and catastrophic defeat. Alan Beckett, whose innovative whale roadway design had proved absolutely essential to harbor operations, offered his personal perspective on the technical challenges they had overcome. He had been a young lieutenant in the Royal Engineers when senior officers assigned him to solve the floating roadway problem that had stumped more experienced designers. The engineering requirements seemed completely contradictory at first examination. The roadways must be flexible enough to accommodate 15-foot tidal variations without breaking apart. They must be rigid enough to support fully loaded military trucks traveling at operational speeds. They must be durable enough to survive months of exposure to corrosive saltwater and severe weather. They must be simple enough to manufacture quickly using wartime production methods and limited materials. They must be transportable across the English Channel in sections that could be assembled rapidly under combat conditions. Each individual requirement alone posed significant engineering challenges that would normally take months to resolve properly. Considered together, they appeared to represent an impossible combination that couldn't be satisfied by any conceivable design solution. He had spent countless weeks sketching potential designs, building detailed scale models, and testing them under laboratory conditions that simulated anticipated operating stresses. The crucial breakthrough came from an unexpected source of inspiration. He was watching a snake move across sandy ground, observing how its body maintained forward motion while flexing at multiple points along its length. He suddenly realized the floating roadway needed exactly those same characteristics. Individual spans needed to be rigid enough to support heavy loads. However, the connections between spans must be flexible enough to accommodate the constant motion created by tidal changes and wave action. This torsional flexibility concept became the key innovation that made everything else possible. Once they had established this fundamental engineering principle, all the detailed design work followed logically. Seeing the whale roadways still functioning perfectly at Arromanches 10 months after D-Day, handling traffic loads far exceeding their original design specifications, provided him with greater professional satisfaction than any other engineering project he had ever completed. An American civil engineer, who had worked extensively on Phoenix construction, emphasized that the manufacturing achievement deserved recognition equal to the technical innovations that received most public attention. Popular accounts focused understandably on the brilliant engineering solutions that made artificial harbors possible. However, the unprecedented industrial production process represented an equally remarkable accomplishment that shouldn't be overlooked by historians. They had manufactured 213 massive reinforced concrete structures in just 8 months, while Britain was fighting a desperate total war against Nazi Germany. Every essential resource was critically scarce throughout this period. Cement, steel, timber, skilled labor, and transportation capacity were all needed simultaneously for dozens of other urgent military priorities. Yet the Mulberry Project received everything it required because Churchill and Eisenhower understood completely its fundamental importance to invasion success. The coordination required was absolutely staggering in its complexity. Concrete had to be mixed to precise specifications that couldn't vary by even small amounts. Steel reinforcement had to be fabricated and positioned within millimeter tolerances to ensure structural integrity. Caissons had to be constructed in specially built dry docks, created from scratch along riverbanks throughout southern England. Then they had to flood these temporary dry docks carefully, float out multi-thousand-ton concrete structures without damage, and tow them to assembly points without catastrophic structural failure during transport. They accomplished this enormously complex process simultaneously at dozens of locations while maintaining absolute secrecy about their activities. German bombers conducted nightly raids over construction sites, yet work continued without interruption. From the humblest construction laborer to the most senior consulting engineer, everyone involved understood they were building something that would fundamentally change the course of world history. a Royal Navy officer who had commanded one of the powerful tugboats responsible for towing Phoenix caissons across the dangerous English Channel, shared his vivid memories of those crucial operations. Each crossing required 2 full days of careful navigation at their maximum safe towing speed of 4 knots. His tugboat had been assigned to tow Phoenix Unit 47, one of the larger caisson structures weighing over 6,000 tons when fully ballasted for towing. The massive tow cable was as thick as a man's arm, yet he watched it stretch dangerously tight under the enormous strain of moving such a massive concrete structure through rough channel waters. Navigation required threading through carefully swept channels marked by floating buoys that German E-boat raiders attempted to remove or relocate during nighttime attacks. They had to maintain precise station within a massive convoy formation while avoiding collisions with other tugs towing their own caissons toward Normandy. The entire English Channel seemed filled with ships of every description. Thousands of vessels were heading toward the invasion beaches simultaneously. The convoy discipline required to prevent catastrophic accidents under these crowded conditions demanded constant vigilance from every crew member. When they finally reached their assigned position off Omaha Beach, precise positioning became critically important. They held station while combat engineers flooded the Phoenix caisson in a carefully controlled sequence designed to sink it into exactly the right location for harbor construction. The controlled sinking process required 6 hours of delicate work, while German artillery observers attempted to direct fire onto the obvious target they presented. Once the caisson settled properly into position on the sea floor, they cast off their towing cables and began the dangerous return journey to England for another assignment. His experienced crew completed 4 complete round trips during 10 exhausting days of continuous operations. They survived on strong tea and pure determination, getting very little real sleep between demanding voyages. Despite their complete physical exhaustion, none of them ever questioned the vital importance of their dangerous work. The emotional reunion concluded with a moving visit to the beaches where Mulberry Bee had once created the busiest artificial port in the world. The participants, now elderly men carrying decades of memories, walked slowly across sand, where massive harbor installations had once buzzed with constant activity. Phoenix caissons, visible offshore during low tide, marked the ghostly remains of Port Winston. Some of the engineers wept openly, remembering close friends and colleagues who hadn't survived the war to see their achievement recognized. Others stood silently, contemplating the enormous magnitude of what they had accomplished during those desperate months in 1944. One reunion participant summarized the feelings shared by everyone present in words that captured the essence of their wartime experience. They had arrived in France 40 years earlier as young engineers facing an assignment that seemed utterly impossible to complete successfully. Military commanders had ordered them to construct a major harbor where none existed. They were told to create reliable shelter from Atlantic storms using only concrete and steel. They were expected to sustain a massive invasion using facilities that had to be assembled in days rather than years. They had been genuinely frightened that they would fail in their crucial mission. They were terrified that their failure would doom the brave soldiers storming these heavily defended beaches. Instead, they had succeeded far beyond their own most optimistic expectations during those dark months. Port Winston had functioned exactly as designed throughout the critical period. Essential supplies had flowed without significant interruption despite constant enemy attempts to disrupt operations. The invasion had held firm against desperate German counterattacks. They had helped win the most important war in human history. Looking back across 4 decades of remarkable technological progress, he felt immense pride in what they had accomplished under seemingly impossible circumstances. They had proven conclusively that engineering ingenuity, combined with industrial capacity and unwavering determination, could solve problems that conventional wisdom declared completely impossible to resolve. The Mulberry Harbors represented their definitive answer to Hitler's supposedly impregnable Atlantic Wall. It was concrete and steel versus concrete and steel, but their concrete floated where needed. Their steel structures bent gracefully with tidal forces instead of breaking under stress. Most importantly, their artificial harbors could go wherever strategic necessity demanded, rather than waiting passively for enemy forces to attack them. In that crucial flexibility, that willingness to innovate, that absolute refusal to accept the limitations others tried to impose, they had found the key to victory over Nazi tyranny. The German High Command had dismissed completely the possibility of major invasion without immediate capture of existing port facilities. They had fortified every significant harbor from Norway to Spain with absolute confidence that Allied supply requirements would make port capture inevitable and immediate. German staff officers had calculated confidently that defending existing ports would be sufficient to prevent any serious invasion attempt. Their strategic assumptions were fundamentally wrong. Allied engineers had built complete harbors from nothing overnight, or more precisely, had built 2 major harbors in England over 8 intensive months, transported them across the Channel in 3 days, and assembled them into fully functioning ports within 2 weeks of D-Day. The achievement was impossible by every conventional engineering measure anyone had previously established. It required technical innovations that simply didn't exist when the project began in earnest. It demanded industrial production that stretched British manufacturing capacity to the absolute breaking point. It needed organizational coordination across dozens of separate agencies and private companies. It meant transporting and assembling massive harbor components while under direct enemy artillery fire and constant air attack. Yet it worked brilliantly when success mattered most. The Mulberry Harbors stand forever as testament to human ingenuity applied under extreme pressure. They represent the ultimate triumph of innovative thinking over rigid conventional doctrine. They demonstrate the power of flexible problem-solving over inflexible adherence to established methods. When confronted with a strategic problem that appeared to have no viable solution, Allied planners had refused to accept impossibility as the final answer. Instead, they asked how engineering innovation could create entirely new solutions that would change the fundamental rules of warfare itself. The artificial harbors of Normandy represent the ultimate expression of what Roosevelt called the arsenal of democracy. They embodied the marriage of technical innovation and industrial capacity that characterized Allied victory throughout the Second World War. More than the battles fought with desperate courage, more than the heroism displayed under fire, more than the tactical brilliance employed by field commanders. This willingness to attempt the genuinely impossible and transform it into functioning reality ultimately decided the war's final outcome. The Germans had fortified what already existed with characteristic thoroughness. The Allies had created what was strategically needed through pure innovation. In that fundamental difference lay the seeds of D-Day success and Nazi Germany's inevitable defeat.